Hello, my name is Ben and I'm a course instructor at the Department of Pure and Applied Mathematics of the Technical University of Kenya. I've been giving a series of lecture videos to help my students in the revision during this COVID pandemic period, and today's lecture is on deducting topological concepts, in which we're going to discuss graphs and topology. So in this topic of graphs and topology, our main objective will be to illustrate planarity of graphs by embedding of these graphs on the surfaces. So having gone through this topic, you should be able to identify complete bipartite and complete multipartite graphs. You should also be able to discuss the various parts on graphs. You should also be able to classify graphs as planar or non-planar graphs, first of all by just doing diagrammatic representations, and also via the embedding of such graphs on surfaces. Then you should also be able to calculate the Euler characteristic of graphs and then deduce the compact surfaces on which certain graphs can be minimally embedded. So we'll use the letter G to denote a graph, and by definition a graph consists of two sets. So we have a set of vertices together with what we call edges connecting these vertices. So we'll say that a graph G consists of a set which called V, whose elements are called vertices, together with a set E of two element subsets of V. So the elements of E are called edges. So for example, so these are examples of graphs. So the first graph comprises of the vertices A, B, C, and D, but then there is no edge connecting them. And the second one comprises of the edge A, B, C, D, the vertices A, B, C, and D, but only the vertex A is joined to the vertex B, and that's why we only have this single, just one, two element subsets of V. And so sometimes it's important to represent graphs diagrammatically. So for example, we'll have the vertices, say A, B, C, and D, with no edge connecting any of them. So the diagrammatic representation for the second graph looks like this. So there is an edge connecting A and B, so there's only that edge. For this third, we have the following case. So there is only an edge which connects C and D. Okay, sorry, so there's a slight correction on this. So let's have this as a five vertex set, and so we can add one more vertex, say C, E. Can add these edges E to D, so that the graph we have looks something like this. So we have A, B, C, D, and E. So there's an edge connecting A to B, another one connecting C to D, another one connecting B to C, another one connecting C to E, another one connecting E to D. Now in this other case, again we have here we have four vertices A, B, C, and D, and so according to the information given, all the vertices are connected by an edge. Now this other graph looks something like this. So I'll put A here and E here, and then B, C, D. So there's an edge connecting A and B, A and C, A and D, and then we also have E connected to C and E connected to D. And then finally, for this last graph, we have A and E, B, C, D, and then we have the following as the edges. One thing that we need to note is that in our case, we'll only be talking about connected graphs. In other words, we'll be talking about graphs graphs in which, at least when you take any two pair of vertices, you will find a path, but we'll define what a path is. Number two, we will not allow, or rather we will disallow multiple edges. In other words, we will not want a case where, say, two vertices are connected by two vertices are connected by two edges or multiple edges. And again, we will not necessarily require our graphs to be oriented, though some of these concepts can be important to someone who is studying graph theory. So let's define equivalence of graphs. So now in our case, we'll say that two graphs are equivalent if they are isomorphic. And now when we talk about isomorphic graphs, we simply mean, if we have two graphs G1 whose vertex set is V1 and edge set is E1, and another graph, say G2, whose vertex set is V2 and edge set is E2, then we'll say that G1 is isomorphic to G2, and that is if there exists a bijection say F from V1 to V2 such that AB is an edge if and only if F of A is an edge in the first vertex set, if and only if F of A, F of B is an edge in the second graph. So for example, these two graphs will be considered the same, and the isomorphism will simply take A to C, B to D, and then probably take C to A and D to B. So we'll call a graph complete if it consists of all possible edges. And what we mean here is, if the vertex set has n elements, then the edge set will comprise of n choose 2, which is n into n minus 1 over 2. In other words, between every pair of a vertex, so we take all the vertices and we pair them. So we take two at a time, and so we end up with n choose 2 number of edges. So the notation for a complete graph with n vertices is Kn. So this is complete graph with n vertices. So as an example, this graph here is a complete graph with 4 vertices, so this is K4. Now we also need to know what a bipartite graph is. and we say that a graph is bipartite. So if we have a graph whose vertex set is V and whose edge set is E, then this graph is bipartite. And that is if, number one, we can express the vertex set as a union of two disjoint subsets. And then number two, will require that whenever AB is an edge in this graph, then this A must be from V1 and B must be from V2. In other words, we can partition the vertex set into two subsets, such that every edge starts from the first set and ends in the second set. And this is an example. This and these are examples of bipartite graphs. So if in addition this bipartite graph comprise of all possible edges from V1 to V2, then we'll say that this is a complete bipartite graph. So if in addition AB belongs to E, or AB belonging to E, is such that A belongs to V1 and B belongs to V2, so it's out of all possible. Then we talk of complete bipartite. So now a complete bipartite graph is denoted by this KNM. So here we simply mean that every edge starts from the vertex, starts from Vn and goes to Vm. So for example, in this case we have a complete bipartite graph. So these two are bipartite, but this is a complete bipartite graph, and this is a vertex set with 2 elements and a vertex set with 3 elements. So this is an example of a complete bipartite graph with the subscripts. Maybe as an example or an exercise, to do testing to tell which of these 3 graphs are Hamiltonian or Eulerian, and in each case display the Euler circuit or the Hamiltonian circuit. But readily, I'll tell you something about the Eulerian graph. As a hint, there's a theorem that a graph G is Eulerian if and only if each of its vertices has an even valence. So when it comes to Eulerian graphs, sometimes it will with the question of telling whether a graph is Eulerian or not, you'll just have to count the valence of each vertex. So for example, this is a vertex of valence 2, valence 2, valence 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. So all the vertices in this graph are even, and so this graph is definitely Eulerian. Now this one is not Eulerian because this vertex here has valence 3, and so even the graph C is not Eulerian. So when it comes to displaying the Euler circuit, again, there's another theorem from which this theorem was derived, and it simply states that a graph admits an Euler circuit, and and that is if and only if it has at most two odd vertices. So when we talk about odd vertices, we simply mean vertices of odd degree or of odd valence. So once again, it will be important for you just to do a spot check to see if your graph is admits an Euler circuit instead of just starting to find one, because sometimes some of these circuits may be a bit involving in finding. So for Euler circuits, for Hamiltonian circuits and Hamiltonian graphs, again, unfortunately, we do not have a stroke of genius which can help us to just tell whether graph is Hamiltonian or just to start finding an Euler circuit, a Hamiltonian circuit, and get. We just have to, in most cases, for beginners, to be just lucky to get that Hamiltonian circuit, especially if the graph is a bit complicated. However, for Euler circuit, there's an algorithm which you can use to find the circuit. So this is what you'll do. So identify starting vertex and edge. So you can call this E1. Then you'll first of all delete the E1 and then choose E2 from a connected graph that remains after deleting E1. So this subgraph which remains after deleting E1 is what is called an allowable subgraph. So you'll continue that process until you get your Euler circuit. Okay, so next we define planar graphs. So a graph G is called planar, and that is if G has a diagrammatic representation on the plane in such a way that no two edges of G cross each other except at common endpoints. So for example, K4, remember, was represented with some crossing diagonals. So if we have a representation in which K4 is drawn like this, so that we don't, instead of having this diagonal crossing this first one, then this is now the planar representation for K4. Now a planar representation for K23, which you had seen before, so it had these vertices. So now what we simply do is to bring one vertex below and then have such a graph. And so this will be the planar representation of the graph K23. So let's also look at embedding. So an embedding of a graph on a compact surface is just a representation of the graph in such a way that the vertices of the graph are represented by points on the compact surface, and the edges of the graph are represented by arcs lying on the compact surface in such a way that no two arcs cross. So we'll say that let X be a compact surface and G a graph. Then you say that G is embedded on X, that is if the edges of G, not edges but vertices, if the vertices of G can be represented by points on X, or should we say in X, and the edges by arcs on X, such that no two edges or no two arcs cross each other except at common endpoints. So another characteristic of planar graphs, we say that a graph is planar. That is if and only if it can be embedded on the sphere. So now it's a fact that any graph can be embedded on orientable or on an orientable compact surface. And so this is how it happens. So if the graph is planar, we can just embed it on the sphere. But then if the graph that does not have a planar representation, then what we'll do is, in order to resolve some of these crossings, we introduce handle. So the handle will be some kind of a bridge which will lift the crossing. So if there's a crossing, if there are two edges which cross, then we leave one edge on the sphere and the other edge passes sort of over a bridge that's a handle on the sphere. So let MT be the orientable compact surface on which G can be embedded. Now denote by gamma of G the genus of X, so i.e. in this case M. Then in this case we'll say that this gamma of G, which is equal to M, is called the genus of the graph G, and we say that this G is minimally embedded on X. Okay, so what we can say again here is that a graph is planar, that is if and only if again any graph that is embedded on the sphere is minimally embedded. While learning about compact surfaces, we learned that the Euler characteristic of a compact surface in terms of genus is 2 minus 2g. And also the same via tilings can be obtained by the expression v minus e plus f. So we want to conclude by making use of these two relations then to show that K5 is not planar. Okay. So now how do we proceed? Now we know that. So if K5 is planar, then the expression v minus e plus f for this graph can be obtained, is equal to 2. It's equal to that one for the sphere. So now we know that K5 has 5 vertices, it has 5 choose 2 edges, which is equal to 10, and so this expression gives the following for the number of faces. So now if suppose this is the case, then we expect the number of faces to be 7. So let's just check that this is not possible. And to check that this is not possible, we know that for any given tiling, the number of faces is given by, so in this case we'll have f3 plus f4 plus f5 and so on, because what we were calling graphs are nothing but complexes. So for complexes we have faces from trigon and so on. So if we multiply this expression by 3, we'll get the following. But now, in order for this to make sense for us to compare this with twice the number of edges, we'll say that this is strictly less than or equal to 3f3 plus 4f4 plus 5f5 and so on. And so this expression here can be compared to twice the number of edges for the case when you talk about complexes. And graphs, the restriction we put to our graphs naturally makes our graphs to be complexes. And so let's see, we have how many edges? We have 10 edges, so on this side we have a 20, and we are claiming that the number of faces is 7, and on this side we have 21, and clearly 21 cannot be less or equal to 20. And therefore, so we'll say therefore f cannot be equal to 7. Okay, so I'll leave it for you to go and to check that K33 is not planar using a similar argument. Indeed, we know very well that K5 and K33 are the obstructions to planarity of graph. So that's it for today. Till next time.